Because it's a buzzword and everyone is talking about it, probably it's a most controversial term in computational science. These days, a lot of people and papers and preprints are uploaded, claiming that they are models and foundation models. A lot of times, their model, goes like this. Working. Okay. Of course, they use the data, right? AI sense, generate tons of the scientific data, and then you train them, with some model. Code is the foundation models. The transformer is very popular in language models and vision models. So people tend to use transformer a lot, and since it's a scientific simulation graph neural network, just to reflect some geometric features. GNN is popular as well. And these days, neural operator, FNO, Fourier neural operator, or depot nets are also popular. I mean, you feed those data and train those models, and once it is trained, you can predict the solutions, unseen solutions, and you can do that pretty fast. So it's good, very good. However, if you change some problem setup, like from one partial differential equation to another partial differential equations, or even when you stay in the same PDE, you change the geometric domain or something else, then a lot of times you have to retrain this model. I mean, people are claiming they can do the fine tuning through the transfer learning and update their model pretty quickly. But I don't think so. Because, I mean, think about this 5D turbulent simulations on tokamak device, which generates like the humongous size of the data. It's at least a gigabyte, if not terabyte, and that's just one single data point. And you will have new gigabytes which reflecting totally different geometry, and need to update these transformers or GNN, and through the transfer learning, you fine tune that model. It takes them hours and hours if it is not days. So it's very strange that the people call this kind of model foundation model, because if you are familiar with the foundation model, actual foundation models like ChatGPT, it's a real time almost. You type on the terminal and the outputs comes in. Well, sometimes they think longer, like 5 seconds, 10 seconds, but it's not hours and hours. You don't have to wait for that, right? So in that sense, it's strange, and probably we cannot call those methods foundation models. But people still do that. Why? Because this currently available foundation model like ChatGPT is basically changing our everyday life. I mean, we are actually getting a lot of benefit out of it as students or faculties or many others. If you're doing coding and the things you had to do, like spend 1 week, and now you can do that with a cloud. You can do that in 5 seconds or 1 minute, and they pretty much give you like perfect code without it's amazing what they can do that. Because it's so popular and powerful, it makes sense that they want to label their model to be founded. Together attention. But even before that, I don't think in computational science community we do not have a agreed upon definition among us. So let's try to define that first. And in order to define it, probably you want to reflect some of the characteristics already exist in the foundation model in AI community. And since we would like to bring that into the computational science, we would like to also reflect some characteristics you must have as a foundation model in computer science too, right? So we have to bring all those features in our definition. So let's go over the foundation model characteristics in AI community. This Stanford group wrote a now like very popular paper. Title is On the Opportunities and Risks of Foundation Models, and in 2022 uploaded in the archive. They define the foundation model as any model that is trained on broad data, generally using self-supervision at scale that can be adapted, for example, through fine-tuning to a wide range of downstream tasks. So it's gotta use the broad data, and those data could be text, images, speech, and structured data, 3D signals, and many others. And you use those data and pre-train your model. And in order to be foundation model, that model should be able to do many different downstream tasks, like question answering, sentiment analysis, information extraction, image capturing, object recognition, instruction following, etc., etc. And this is, the definitions they use. And if you experience how they work, it's a lot of times you are very surprised with some sort of emergent behavior they can do, right? They can actually do the stuff which they haven't actually seen before, right? So this Tom Brown, currently in Anthropic, they describe those emergent behavior in their paper, even before the Stanford guys, the paper in this, the title of language models are few-shot learners. If I paraphrasing their description of this, they didn't call it foundation models, but the GPT-3, for example, they said the unprecedented scale of GPT-3 using 175 billion parameters has shown that large language models can generalize to a wide variety of tasks without task-specific training. They adapt at inference time through natural language prompts or a handful of equations through few-shot learning, achieving reasonable performance on many tasks they were never explicitly trained to do. And people are generally very impressed by this emergent behavior. And if you describe that emergent behavior in other words familiar to our terminology, it would be described as generalizations, right? Trained on one specific type of data, it should be generalized to many other tasks. Yes?
So some people call it in-context learning. So you have a prompt, and the trained model is able to read the prompt and produce a result prediction without updating the weights, no weight updates. And that is, some people call it few-shot learning, people call it context learning. So I think there's a potential for scientific computation. We have a paper, yes, but yeah, so in context learning is this phenomenon. Nobody actually understands it very well. But they have a paper with PD solvers, in context PD solvers, or Osher from San Diego, I guess.
Osher is from UCLA.
UCLA, yeah. So he has a paper on, like a PD solver in context.
Yeah,
just a comment. No, it's not a question. It's just.
Yeah, it's fine. Yeah.
No, regarding does it mean that the hyperparameter don't get optimized again in the fine tuning?
They do fine tuning,
So
but it's done very fast.
So in optimization perspective is that if you find a good starting point for the optimization, you spend a lot of time with other data for a good point, and from there you're able to find different minima. depending on the
and very fast. Yeah.
and very fast.
So in numerical optimization terminology, it could be a warm start,
Yeah.
cold start. Yeah. So all this terminology, what the few shot learning, and you said in context
learning.
in context learning, and yeah, different community come up with their own terminology. But if you talk about it, they are talking about the same thing.
Same thing. Same thing. Yeah.
Anyway, the point of this slide, what I was getting at is, okay, from AI community, this emergent behavior they didn't see before. Now, like the large language models and vision models, they started to see that. And in order to, if you want to define a foundation model in computational science, you gotta include this generalization terms in it, right? So that's the whole point of this slide. Okay, so how about the computational science? Well, when I say computational science, I'm assuming you guys are all working on computational science. Maybe I'm wrong. Is there anyone else? Someone who's not working in the computational science here? Probably not. Okay, I was right. Okay, good. So, okay, we are friends. Computational science, I mean, we do have foundational math, right? Finite element method is one of them, very popular and powerful. Finite volume method for usually computational fluid mechanics, dynamics. Finite difference method, also the fluid and many other partial differential equations, and spectral method, which is really powerful in seismology community. All these methods are called foundational, and because of reasons, they have, two or three features which to be called a foundational, and they're very justifiable. So the first feature is universality. All these methods, for example, if you look at the finite element method, underlying structure doesn't change, even though you solve structural problem or fluid problem, electromagnetic problems. Underlying structure is reformed, right? You have a PDE, introduce the test functions, integrate, and form a reform and discretize it, and using polynomial data and solve it, and that structure doesn't change whenever, even though you change the boundary conditions or anything. So that universality is one of the reasons why we call those methods foundational. And those methods are supported by great mathematical analysis, thanks to these great mathematicians, Hilbert, Courant, and John von Neumann, like convergence analysis, stability analysis, and a lot of error analysis, which is actually helping us to develop more sophisticated algorithm, like adaptive mesh refinements can be developed using some error analysis, error indicator, etc. And those analyses can help us to decide which solver to choose for specific problems. So it's very helpful. It's supported by great rigorous mathematics, and also a lot of times, software engineer, computer science people these days, AI agents like the ChatGPT, some of those code as well, but not in mature level, I guess. But once it is implemented with the C++ code or for example, whatever, and if it is implemented right in user-friendly way, then you do not have to re-implement things in order to tackle different types of problems, right? You only need to change the geometry mesh, like refinement of the mesh and material boundary conditions, and you can still use the good chunk of the underlying foundational code you have implemented for FEM or FEM to solve different problems. I mean, there's a problem. A lot of times it takes long, very computationally expensive. But the point being here is once it is implemented, those domain scientists comes in and they only look at the input back and change some numbers here and there, and they can solve many different interesting problems without actually needing to go into the code and then understanding what's going on it, right? So those features is like, probably there are many other reasons why we are calling these methods foundational methods in computational science, but I would say these three features are key three features. And when you define the foundation models in computational science, you probably want to include these features in the definition. So that's what we try to do in our listening paper. And the title of this slide is our definition of foundation models. How can I get rid of that? I don't know.
Just click. It's on the other. Just click OK.
What?
Just click OK.
On the other computer.
It may be on the other computer.
Is that right there?
No.
No, it's all. It's
Okay, cool. Okay, cool. So here's the definition we came up with. Let's see, you're gonna agree with that because you guys are all computational science guy, and look at this. Please evaluate that on the lens of the computational science background you have. Okay, the foundation model in computational science is a data-driven model trained on a broad distribution of scientific application types of physical systems. This exhibits wide generalization capability across scientific problems, computational domains, tasks, and physical conditions without requiring retraining from scratch or structural modification, and serves as a reusable base. Okay, so there are probably 5 different features we have included in the definition. So let's try to look at it one by one briefly. The first feature, of course, it's gotta be data driven. Otherwise, in AI sense, it's not foundation models, right? And those data should come from broad, diverse contexts. So in computational science, it could be the data coming from maybe Stokes, Maxwell, wave, transport, Poisson, and so on, from many different physical systems, right? You collect all those data together and come up with some model and train that model using that data, and that model should be able to have a generalization capability, which we just talked about and 5 minutes ago. And in the computational science context, that mostly what do we mean by the generalization capability? That model should be able to solve various the problems with the diverse boundary conditions, not only for one boundary conditions, should work for varied parameters, and not only for the form simulation, but also the inverse problems, and not only for the single physics, but multi-physics problems. It should work for many different equations, probably all of these equations with one single model. And geometry should work for different geometric domain, and not only for the deterministic problems, but also for the uncertainty computation. And the scaling up, I mean, your model not only should work for small scale domain which you have trained your model for, it should work for much larger scale problem as well. Because I mean, a lot of times we are dealing with a multi-scale, right, problems. I was talking about the Jian while we are coming from the lunch here. Yes, I mean, that's why this problem becomes hard because of the scales. Okay, so that's a feature you must have, and all of this should be accomplishable without retraining from scratch. I mean, you could do some fine tuning, but the fine tuning has to be done really fast. It shouldn't take hours and days to do the fine tuning. No one is going to use your model if it takes that long. Oh, and then of course reusability should be reusable. Those models should be reusable. Okay, in addition to those 5 features we included in the formal definitions, we have listed 4 more, 4 more desirable features just to reflect, some features in the computational science. So the first one is obvious one is scientific consistency. A lot of times, yes, I mean your predictions from foundation model should physically make sense, right? I mean, you could make it visually appealing, right? The ocean simulations, the wave simulations. A lot of times, the Hollywood use those fake the images, but to use from all the scientific applications, it's your quantity must conserve some mass, energy, momentum, or maybe your problem has some symmetric features you have to hold, and non-negativity, and etc. etc. It has to preserve those physical quantities, right? Your foundation model should be able to do that if you want to be called foundation model in computational science. And just like the finite element method, it can be supported by rigorous mathematical analysis and theory, and then that will in turn help us develop further advanced our foundation models, not just using data. You should be able to come up with some convergence analysis of this foundation model. Now, since we are dealing with the data, what kind of data, how much of the data is going to help us achieve this level of accuracy, etc. And if you have some sort of the analysis there, then the analysis is going to help back. If we sample this and here and there and there, then we probably don't need big data. Maybe we can minimize the number of data that way, right? So the mathematical analysis is supported by mathematical analysis. That's sort of the foundation model is very desirable. Of course, the robust extrapolation, I mean, that's another words of the generalizations of computational science. And in data-driven method, a lot of times your predictions only works in interpolative regimes. If you go outside of the training regions, a lot of your model does not work, right? A foundation model is all about the generalizations. It should work. I mean, those emergent behavior I talked about, right? The things you haven't seen in the training, your foundation model in computational science should be able to, give you pretty accurate solution too from outside of that training region too, right? So that's what we mean by the robust extrapolation. And one more is very natural one, since it is data driven. As you include more and more quality data, your data should improve and improve and improve. That's what we meant by the data scale. Okay, so definitions, desirable characteristics of the foundation model in computational science. This is all good, right? Fantastic, sounds awesome, but is it realizable? Sounds almost like very daunting if you know how computational science works. I mean, at the end of the day, computational science is very different things from Gosseling's models or fusion model. I mean, if it was easy to realize, those foundation models which we defined, then probably someone else already had done it. And why is it so particular what is so particular about the computational science which makes the building foundation models so difficult? And it's because computational science poses several challenges, and one of the challenges is a massive data point size, which I have already talked about, like with the 5D turbulence simulation for tokamak. Every single data point is gigabytes. If it is not parameterized, handling those data give us the difficulty of building efficient foundation models. Because of that, the expensive fine tuning you need to do, it's hard to accomplish the real time fine tuning, to be like the ChatGPT, And data heterogeneity, ideally, your single trained model should be able to handle, some of the data type or specific problem, like it could be scalars or vectors, matrix or tensors. Depending on the applications and PDE types, those data types are very diversely different, and handling all those different data types with a single model sounds fun, right? And also, unlike the large language model or vision models, we do have a lack of standardized data sets. I mean, for the text and the images, you just grab the data from the internet or textbooks or and then reposit. We can create some shared repository, and that's what they have done, like with the ImageNet or some text data. And people from Toronto and all over the place, and they can come up with their own models and use the same data, and they can actually compare and which one is better in what sense and all that. For us, I mean, pretty much up to today, what we have been doing is we have our own data. A lot of times we generate our synthetic data generated by our own group, and we do not tend to share those data with other folks. I mean, we try to do so, but it's hard because although you're solving one Navier-Stokes problem, your discretization would be different from this group's discretization roadmaps, and it's not compatible. The data is not comparable. So it's very last meaning of what do you mean by standardized data sets, right? I mean, there are a lot of obstacles you have to overcome, and that slows down the development of the foundation model. Well, the mesh and geometry dependency, a lot of times the computation science have very diverse mesh and geometry you have to handle, even if you're dealing with one type of the PDE. And coming up with a model which is consistent with the physics, underlying physics, it's not fun. So some of you have experience with that, and because of that, the black box model is out of the candidate to be a foundation model, because a lot of black box method is not giving you physically consistent predictions. And multi-scale and long time behavior. Probably when you do the training, the training data will be limited by the short time and small scale. Because if you want to generate a lot of data, you probably deal with a small scale and then short time. But you should be able to generalize to not many other scales and then longer time, and that's really hard to do. So after all the challenges listed, and it sounds like it's impossible to come up with a foundation model that satisfies that desirable characteristics I have just introduced to you. So in the paper, because of that reasons, we had to at least introduce one framework which can realize this foundation model in computational science, and that's called the data-driven finite element method. And the name implies that it's definitely inspired by the traditional finite element method. So to set the stage, let me briefly go over how the finite element method works. I'm sure you guys all familiar with how the finite FEM works. What do? You select an elements. Let's say you have selected the tetrahedral elements, because it's very famous structure elements. And you assign a polynomial basis, right, to represent the solutions within that element, right? And then you assemble those elements together, form some complex geometric domains, and then you solve a underlying governing equations numerically, and that will give you the coefficient in front of the polynomial basis. And once you get the coefficient in front of the basis, now you can represent solutions anytime, any solutions for any complex problems. And as I mentioned, this FEM is a foundational method in computational science because it's very powerful. You can solve virtually any complex business problem with high precision. Obviously, it's supported by the mathematical rigor, and there are many software, commercial software out there, and the company which actually make money out of it, right? And because the pen is so powerful, and probably this Texas A&M also teaches the FEM course in undergrad or graduate level. Graduate level? Okay. You teach it, John?
No, in math, but we
In math? Oh, okay. Not the engineering department?
we also teach in budget level in engineering.
Or mechanical engineering.
Mechanical, yeah.
Mechanical engineering. Okay. Yeah. So
Everywhere.
everywhere. Not only Texas A&M, but pretty much every university dealing with engineering or some sort of science, computational science major, they probably teach this course at the end because it's powerful. And not only the academia, like the Lawrence Livermore National Lab I belong to, rely heavily on FEM to simulate very complex problems like powder bed fusion, pore collapse, and 3D shape charts, and many other complex multi-scale, multi-physics, and multi-phase simulations. We use FEM to solve those problems. So that's good. So do we not need a foundation model? Why do we even talk about the foundation model? And because all these simulations, as you can see, although it gives you very detailed, accurate, precise, complex solutions, it's computationally expensive. Even using the fastest high-performance computing machines we have at the lab at Hackathon, and it takes like, even using many cores, it takes 1 week and days, and just for one fold simulations. So, I mean, a lot of times you want to simulate a lot more than one simulation, right? In order to explore your camera space or solve the design problem, or etc. So this is very unfortunate. And if you think about why, it's because your basis you're using is polynomial basis, and polynomial basis is generic form. It does not know anything about your problem. So in order to improve the accuracy, you have to use the very small element size, like fine mesh. Or if you want to keep the size of the element bigger, then you probably need to increase the order of the polynomials and higher. And either way, the resultant problem size is going to increase a lot and becomes million, billion, trillions, and solving that system of equations every time or every little steps, and that's costly. That's why it takes like 1 week or days. So in order to address that, this data-driven finite methods nicely replace that polynomial basis, which does not know anything about the problem, with data-driven basis. And conceptually, you can think, oh, that's nice, because the basis, data-driven basis, is constructed looking at the data, and the data coming from physics, right? So in some sense, indirectly, this data-driven basis knows what kind of physics problem or engineering problem you are going to solve. So the quality of the data-driven basis is going to be better than the polynomial basis. Because of that, you can take the larger size element, and because it's a larger size element, you can take the larger time steps, so you can solve larger scale problem and longer period simulations and so on. And the rest of the procedure is similar to the finite method. You assemble them and solve the underlying governing equations. So it does use not only the data, but also use the physics. So it's a nice integration of the data and the physics. A lot of benefits comes with it, and the obvious benefit is the training. Because the data-driven basis does not need to represent the solutions for the global domain, you only need to represent the solutions that local element level or the subdomain level. Generating the data on that local small level is very, very cheap, right? You can do that a lot of many times and generate tons of data, right? And that's a good thing from the perspective of AI, big data. It will improve the quality of your data-driven basis, right? So, and then once you get these data-driven basis representations, assemble them, and those augmented basis representation is going to represent the solution in the global domain. So once it is trained, that can be reused as long as those computational domain can be, constructed with already pre-trained data-driven elements. So that's the concept. Okay. If you go into some more details how it works, of course you have to generate the data, but you don't have to generate the data in the global domain. You can generate the data on the patch level, right? The small scale level. It could be square domains, and you could also generate the data for many different PDEs. PD1 could be Navier-Stokes, PD2 could be Maxwell's equation, PDE, and could be transport equations and many others, and generate many data. And then the next slide, I'm going to describe how you come up with the data-driven basis. But let's say you have constructed a data-driven basis on the small domain, and then you assemble them to form a much larger scale domain, like this little thing is corresponding to this one of the data-driven elements. And of course, you have to assemble them, and sometimes you can distort the element, just like what you do for the traditional finite method. You can come up with some mapping from reference domain to the computational domain. You can also do so for the data-driven basis. And when you do the assembly, just like the traditional finite method, you could do the conformal assembly or non-conforming assembly, just like the discontinuous Galerkin. So there are many different variants of this framework that you can apply, inspired by the traditional finite method. And once you assemble them and you actually solve the underlying governing equations, and when you, for different governing equations, you will obtain a different type of the system of equations you have to solve. But at the end of the day, you will get some sort of AX is equal to B you have to solve. And that X unknown is either coefficient or the latent representation of your data basis. And once you get that by solving the governing equations, this is problem. Now using those data basis representation, you can reconstruct any solution, any time and any space, just like the traditional finite element. That's how it works. And there are many different ways of constructing the data-driven basis. I'm going to show next slides some results of using compression-based approach. There probably a lot of you is familiar to you. You could use POD, or you could use autoencoder if you want to improve the expressivity. And basically the idea is high dimensional. Although you are dealing with a small scale problem, that's a high dimensional vector to the small dimensional space, and use that as a unknown space, right? That's the idea. Or you could use the symbolic or sparse regression based approach, and using data, you can try to come up with some functional form instead of the compression based representations. The advantage of that is because it's a functional form, you could probably integrate that and augment that data-driven functional basis forms with the traditional polynomial basis functions, and complete realize the concept of like extended finite element or the generalized finite element, and all sorts of the play you can do, right? These days, the neural operator or the implicit neural representations, which maps actual physical coordinates and time, into the actual the physical the state outputs. That's very popular these days, and you could take that phone as a data-driven basis in the DDFM, and in that way your method becomes the non-grid dependence method, right? All those traditional method is kind of still depending on the grid, but by taking this type of data-driven basis options, you can turn your method to be non-grid within the each element, the data-driven element level. Okay, before I introduce actual numerical results, here are some analogy between the NLP and DDFM. So if you think about it, the natural language programming, you take the text data, and what they do is they break down into the small pieces, so-called the token, and they vectorize it and handle it numerically, and that's kind of the top down, right? And you have some global representations and break it down into the tokens. And then what they do, what do they do? They use some attention mechanism or reasoning mechanisms to construct the new text or a new paragraph or a new code which it hasn't seen before, and use that in large language models. And if you think about it, DDFM does the similar things. You have a global domain, you like to solve the physical problem, you break it down into the small pieces, and then that's the top down, and you can also do the bottom up, and you build a data basis of each element, and then assemble them and solve the global governing equations in the global domain. That's the bottom up. And because of this analogy, probably it's now you can somewhat easily see that this DDFM could be foundation modeling in computational science. If you all agree with that, I can end my talk here, but probably not. So just to show you some numerical examples, the next few slides, I'm going to show some features of the DDFM, realizing those characteristics we have included in our definition of the foundation model. The first feature I would like to demonstrate is the extrapolation in space and extension to inverse problems. The first example is a lattice type structure problems, where we introduce two different components, struts and joints. And how we're going to use those two components is to form some lattice type structure. And in this lattice type structure, this joint is used, many joints are used to connect the different joints. This strut to different joints and form the lattice type structure. And here, it's, following the DDFM framework, individually in each component, in order to generate the data, we discretize further in this component, right? As you can see, this tree, and apply the different parameterized boundary conditions of this on the surfaces, and generate. You solve a linear elasticity problem and generate many data on that components. Okay, and use that the data, and we use the POD type of the data, the compression technique to come up with a data basis, and use that data basis in the assembled global domain, and apply the pressure force and the boundary conditions, and we solve this displacement analysis or the stress analysis, which you typically do in civil engineering or the structural analysis community. And when you compare the performance, if you use the traditional finance method, with this level of the discretization, you need a 2.7 million degrees of freedom for this particular instance of the problem. But if you use the DDFM, because you compress that in component level, the number of degrees of freedom you have to solve is around 4,000. And because of that, we were able to obtain thousands of the speed ups and the accuracy is pretty much non-distinguishable. You achieve a relative error less than 1%. And because it was so fast, right, we were able to use it in inverse problem, design optimization problem. And this video is showing that, this lattice structure, given these boundary conditions and the pressure force, can you minimize the weight by eliminating some of the components, right? And that's basically topology optimization problem, minimizing weight under some stress constraints or some compliance constraints. And we were able to solve that using this DDFM and still get the 1,000 speed up and with a less than 1% relative error. And this video is actually showing the optimization process starting from keeping everything or eliminating some of the blue regions and keep only the red regions, and it's makes sense, right? It's connecting the forcing spots and the boundary conditions, and yeah.
So how many additional data points you need to collect to get like a relative errors that small?
Well, we not additional, but we didn't even need to retrain those data-driven bases in order to solve the inverse problem. And the next slide is we actually extended that to the much larger the lattice structure problems, and we didn't even need to add additional data to solve these different types of problems. Just the pre-trained data-driven basis was sufficient to solve this diverse, inverse problem and a problem with a much larger, bigger domain problem, etc., etc. It could be all. And initially, we use a lot of data. Yes. So for individual training on this each components, I think it's more than 1,000 data points we use.
Do you need oversampling when you generate the basis?
Oversample, yes, big data. I mean,
No, what I mean, sorry, is that like you are building an element for example, for the joint. When you generate the basis there, you have to run the simulation on a larger subdomain of your structure and then just cut off, so to forget the boundary conditions.
Oh, okay. So I'm skipping the details. So actually, for this type of problem, there is a basis for the interior, and there's a basis for the interface.
Okay.
So I mean, I know you have a very strong reducible model background. So do you know the Tony Patera's MIT groups?
One with Smetana, Katri Smetana.
SCRB methods.
Localized
static condensation. Basis method. Basically, it's that. Like exactly the same framework.
Okay.
So this SCRB, some people call it component reduced model. That is a one instance, special instance of the DDFM. You can view it that way. So it uses the POD as a basis, and also the assembly, the part is conforming because you are using the interface basis and the interior basis, and interface basis is shared by the adjacent, the component, right? So I construction is continuous. So that's that kind of. So it's a but it doesn't have to be. So next examples, we did not use that SCRB here. We use the discontinuous Galerkin type of assembly, so that we don't even need to construct the interface basis. We only need to construct the one basis for each element, and intentionally introduce the discontinuity between. But throughout the solution process, we try to minimize those discontinuities, just like the DG in finite element. So the previous example was linear time independent problem. How about nonlinear problem? Yes, you can still apply the DD problem, and porous media, the negative stock situations. That's illustrations, and there, because it's a porous media simulations, we parameterize those elements with different obstacle shapes, and so that flow can go around different types of obstacle shape, and just follow the same the DDPM the procedure. Here we still use the POD basis, but we did not have to build the interface basis, only the one basis for each element, and glue them together, and you solve these Navier-Stokes equations, and with some boundary conditions, inflow and outflow, and you get 25 speedups, not as big as the thousands, but still significant speedups, and that's then 1% relative error. Yeah.
When you mentioned the speed of the system count with time to generate and train,
So think about that. Okay, so the training is on this small scale. And what do you mean by like including the training cost to solve this bigger problem? So there's a like some mismatch here, right? And so we didn't include the training. But the thing is, once this data-driven basis on this each element is constructed, not only you can solve this specific instance of this porous media, you can randomly change the distribution of the shapes and then solve totally different problem without retraining. And even you can make it larger and then solve the totally different problem. So I guess we are justified not to include those training data. Yeah.
For the construction of the localized reduce basis, are you varying the boundary conditions, or for example, there that you have different shapes, so you assume that also the parameters of the shape?
Yeah, we use the different boundary conditions. Yeah, I'm skipping the detail. We do not actually use the single element and train it. We actually combine like 2x2 subdomains, and when we construct that, different arrays of the configuration of the obstacles, randomly generated, and we change the boundary conditions.
Is the obstacle parameterized, or there you have a family of different possible obstacles and you train?
Different family of the obstacles, yeah, and it's kind of the library. And whenever you need certain obstacle shape here and there, you just grab it and then put that and use that and assemble it.
In principle, you could also parameterize the shape.
Yes, make it bigger, or also the location of the obstacles could move within this, domains, etc., etc. Yes, exactly. Or, as I explained before, this could be considered as a reference domain, and in the computational domain, you can actually distort that and through some mapping from reference to the computational domain. All those techniques we already use in traditional finite method, it can be used, extended to the DD-Tran framework as well. In order to demonstrate and implement that, we need the people, and I hope Professor A&M is interested in this and we can work together. For sure, John, the next, 3 new, that whatever contract, subcontract, we definitely, yeah. But not just John, we need more people. So, okay. Okay, so how about the time-dependent problem? It works as well, and this is the demonstrations. And for this time-dependent problem, we intentionally use the advection-dominated problems, and typically advection-dominated problem, POD basis is not good. So we use the neural net, autoencoder type of the basis, and just to overcome the challenges posed by this advection-dominated problems. Well, here there's no obstacle, so we only needed one data-driven element, and for the training, construct the 2x2 subdomains, and we had to impose the periodic boundary conditions. Otherwise, it's going to vanish. And here you will see that after certain reasons, the solution vanishes if you don't impose the periodic boundary condition. But after the periodic boundary conditions, it looks very smooth and realistic, and even the global domain. And for this particular problem, we obtain 1,000 speedups and maximum 1% together. And the surprising thing about this demonstration is that, if you are dealing with a nonlinear problem, And now we are using the autoencoder type of neural net basis. And we are actually increasing the nonlinearity, right? So when you actually apply, the physics and, the technique from the projection-based reduced model, usually you need the technique called the hyperreductions to achieve, efficiency. But as so far, we did not need a hyperreduction for this, and we still get the thousands of the speed up. That was very surprising, and I think the reason is that the nonlinearity all contains in this small element, data-driven element. So for those small elements, those nonlinearity does not introduce too much computational complexity. So even without the hyperreductions in the global domain sense, we were able to still get the thousand speed up. And that when I present this into the domain decomposition finite element method expert guide, and they were kind of understanding, oh yeah, that actually he actually have seen the kind of phenomena in traditional domain decomposition finite element method context as well. So I was, oh, that's great, because implementing the hyperreduction is, I don't know, it's a but you have to go into the source code and then do a lot of bookkeepings, degrees, each degree wise, and if you don't have to do so and still get 1,000 speed up, that's great. Okay, how about the generalization to the different source functions? Let's train the specific data-driven elements using these source functions, sinusoidal source functions. And if you just use the same source functions and just make it much bigger in the domain, of course it's going to work. But how about different source functions, right? Instead of just the sine, about cosine, and also introduce some exponential function, and also make the solution in a way that it's spiral, not so much of the straight. And it still works. It gets like 0.7% relative error and 1,000 times speed up. So we were able to get. How about generalization to different PDEs? And in order to demonstrate that, we didn't collect the data from extensively diverse PDEs, but just for the sake of the demonstration, we use the generated data for Poisson equations and Borger's equations, representing parabolic equations and hyperbolic equations, two different PDEs, right? And build a single data-driven basis. And using that single data-driven basis without retraining, we were able to, of course, solve the Poisson and Borger's equations. We haven't tried to solve other types of PDEs, but if this data that's used to generate the data basis is diverse enough, there's no particular reason why it should work for other types of PDE as well. So that would be very interesting to see. Of course, the extrapolation for much bigger space, that also works. And okay, so that's pretty much it. I guess I have went over time. Sorry about that, but this DDFM, hopefully you agree with that. It could be really a foundation model in computational science. It enables a local training and global assembly. I have shown some cross-domain generalizations, and of course, once it is trained, it was reusable, and also demonstrate the space-time extrapolation. And since it was solving the physics problem at the end, the solution was very scientifically consistent, right? And those mathematical analysis, which is available from traditional finite method, it could be, very useful for DDFM context as well. So it is supported by the mathematical analysis. And there are many things still to actually make a foundation model DDFM. And preconditional is one of them, because if you introduce millions of different data-driven elements in one system, the system of equation you have to solve at the end of the day is humongous, and so you need a different types of preconditioners to make that conversions faster. And the structure of that system is different from the traditional finite method. You need a new preconditioner, unfortunately. So some research needs to be done, and many others. And here is the preprints I was talking about before, and these are getting a lot of attention these days. Lawrence Livermore is interested in. They put some article about, wrote an article about it, and also HPC wire versions is available online. And some people who are interested in this work, and also they came up with this blog writing. And I recently did a podcast with Sarah Webb, the Science in Parallel. You can check out this podcast. And actually, Justin Hobbs, I just met him. I never met him in person, but I met him in LinkedIn. He's pretty popular, popularizing and advertising some of the emerging the algorithms in LinkedIn community, and he has his own blog and podcast series. And one day he sent a message to me, and Youngsoo, I'm pretty fascinated by your paper on foundation models, and I actually made a podcast out of it. And he shared the link, and I listened to it. It was actually very professional, and I checked all the content. It was all accurate, and then I was like kind of proud of myself, and actually made one of my daughter listen to that. And as soon as my daughter listened to that, she was saying, "Oh, this sounds like ChatGPT." Oh, yeah, you're right. That sounds like a ChatGPT. And then I go back and his webpage, and he did say this podcast was generated by AI tools. But I mean, I was so impressed by it. See, like this foundation model in AI world, what they can do. I don't know. They can make pretty big stuff very accurately. I don't know if it's good things or bad things, but I don't think. Someone made a YouTube out of it using AI tools as well. Not us, someone else. Yeah, and all that. And so Librem team in Lawrence Livermore, we have some resources available. Probably you guys don't need this one because you guys are already pretty familiar with the computation science. But if you're not, then this resource will be pretty useful. GitHub repository, many open source code, which many algorithms which I haven't presented here today is also in this GitHub repository, and we have our own web page, and we try to explain what all individual algorithm does, and what it's good for, what type of the problem, etc., etc. And we do have a for some of the open source code, it's a C++. Always the compiling C++ is so we made a compiled version available in the AWS. So if you don't want to deal with the compiling the C++ codes, you can just go there. If you happen to have account there, go there and then just generate the data with compiled versions. Which some of the examples I have shown today is actually use those C++ code, so for the scale of yeah, some funding, the support recognitions, and I promised, one of my colleagues at Lawrence Livermore National Lab, Daniel Ossekofer, in computing directory, who's like computational molecular dynamics person, but he's also charged in this FONBAC postdoctoral fellowship we offer every year at Lawrence Livermore National Lab. It's a great opportunity if you happen to be graduating soon and looking for a job postdoctoral position. This FONBAC is giving you a lot of freedom. If you are selected, then next 2 years you can do whatever research you want to do, pretty much complete 100% freedom. But because of that, it's very competitive, but yeah, please apply. I think the deadline is the November 20 something, so you guys still have a time, if you're interested in this opportunity. So I promised Daniel to advertise this when I told him I'm going to Texas A&M, and he was like, oh yes, please advertise this. Yes, I will. And with that, let me conclude my talk.
Right, let's thank our speaker. We have a couple of questions asked and answer during the presentation, but if you have a couple more, feel free to ask. We have some time for one or two more questions.
The basis extraction, you said POD.
Sometimes neural net, yeah.
Oh, neural network. I don't want to take any file, steal any file from any mathematicians here, but are there other paradigms like, some sort of energy norm or some sort of, something more involved than just doing data compression?
Just POD?
Yeah.
Yeah. I mean, once you go into the neural network encoder, the concept of the energy norm it's not there. And like, because of that, what would be the optimal latent space, like the reduced space dimension? I mean, for POD, it's obvious, like energy norm gives you like a sense of what complex dimension will be good for your application. But as soon as you go to the autoencoder, that concept is lost. So a lot of times we just use the trial and error and start with a very small dimensions, 3 or 4. If it doesn't work, then gradually increase that. So yeah. So a lot of research needs to be done in that sense.
On these, I've been using spectral greedy methods and randomized greedy methods for
Yeah.
selection alternative.
There's the guy in Reusable National Lab who actually got the 1-year LDID funding just to look at that, automatically find out the optimal latent space dimensions for given data with the autoencoder frame of sense, and he came up with some I forgot, like some postulations, the techniques to automatically find out the optimal dimensions. So some effort is going on there to address that issue. I have a question for you guys. So the definition I introduced you guys, like the data-driven finite the definition for the foundation models in computational science. Let's go back there. How do you like it or dislike it? Do you think it's reasonable? Like this, some form of definition we try to put for the computational science community? Are we missing something, or is too much things included?
If I may, I think in reality, when you're
Reality.
manipulating data from the real world scenario, the incoming data is always limited. The sensors you cannot deploy that many sensors. You really have a limited number of sensors you can deploy. And so it will be very, very sparse. And how can you address that in this data-based basis?
So in that context, you're like collecting the data from real experiment or the digital data. Yeah. I mean, this is like, I mean, the GDFM context is resolved pretty well because it's all synthetic data, and you have a freedom of generating what kind of data you want to generate. So we do not have the challenges. But for some other cases, probably you have those sparsely sampled but however, somehow your foundation model, just like the GDFM, if you can come up with a localized data, right, and hopefully that localized data, even from real field, you can extract much densely manner because it's localized to small regions, and you concentrate on entering the data on not the whole global field, but the small, and that way the sparsity issue can be mitigated. I don't know. I'm just
Yeah,
thinking out loud and, yeah.
I can talk to you on our way to the airport.
Oh, you're gonna give me the.
Yeah, I'll give you
right?
that.
Oh, awesome, okay, cool. Oh, yeah.
One more question, I think since we already, one more question.
Oh yeah, just a comment about the definition. When you
Please, please.
when you were describing it, it came to my mind a letter from Isaac Newton. I think it was 1675, if I remember correctly, when he writes, "We're standing on the shoulders of giants." Essentially, it's this the concept, right? That you say like, we are not wasting what is the past. We're really like, it's so general, it's almost philosophical. That's a bit what I'm afraid.
Oh, yeah.
I want you to say that.
Yeah, exactly, yeah. I mean, so general, I mean, definition, definition, usually it's a pretty general, that's why it's called definition. That's why we had to come up with, at least to show this DDFM framework. Since it is so abstract and general, I mean, is it realizable, really? So I'm here just giving, okay, DDFM, yeah, could realize this definition, yes.
But this is much more broad, I feel, that the
Yeah, exactly. DDFM is probably can be categorized as a foundation model for PDE, partial differential equations type of computational science, but computational science is much broader than just PDE, right? Yeah. Well taken. Thank you.
Good, let's thank our speaker again.
Oh.